Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Chemical Deposition Techniques from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, the fundamental physics of the chemical deposition techniques will be discussed. Second, we will get to know about the different chemical deposition techniques being employed in the modern world. Next, we will discuss about the detailed analysis of the frequently used chemical deposition processes. So students, let us start with a basic introduction about the module. Chemical deposition techniques play a very crucial role in the design and manufacture of several useful devices. These techniques are employed to produce high quality and high performance solid materials. They are mainly used to produce thin films. These techniques helps in overcoming several drawbacks which we observe in physical deposition techniques like poor conformality, low throughput, restricted directional variation, and reduced compositional control. This field is dominated by mainly two groups. The first group comprising the chemical vapor deposition CVD and atomic layer deposition ALD. Both these techniques comprises of a process in which gas phase is used to transport volatile molecules to the surface serving as substrate. The second group having technique known as chemical solution processing or Sol-Gel processing, which uses liquid phase as the mass transfer media. In both the processes, the basic technique employed is the same. The final material in both the cases is created by the molecules of chemical compounds which are being served as precursors as shown in this figure. Precursor is the one of the compound that participate in the chemical reaction that produces another compound. These precursors are directed to the substrate surface and chemically modified to obtain the desired film. So we will study about the two groups in a bit more detail in the following sections. Chemical vapor deposition. In this process, the substrate, often referred to as the wafer, which is placed inside a chamber, is exposed to one or more volatile precursors, which gets deposited on the substrate to produce the desired film. Since there is a chemical reaction involved, so very frequently byproducts are released, which are removed by gas flow through the reaction chamber. In micro device fabrication, CVD is widely used to deposit materials in various forms such as monocrystalline, polycrystalline, amorphous, and epitaxial. The materials which are often deposited by CVD are sulfides, oxides, nitrides, carbides, silicides, etc. So students, this figure shows the fundamental sequential steps of CVD process. First, the transport of reactants to the reaction zone. Second, chemical reactions in the gas phase. Third, transport of reactants and their products to the substrate. Next, the adsorption and diffusion on the substrate surface. Then there are heterogeneous reactions catalyzed by the surface leading to film formation. Next, the desorption of the volatile byproducts of surface reactions. Lastly, the transport of the byproducts away from the reaction zone. Types of CVD. CVD or chemical vapor deposition is divided into several categories based on different criteria, which are as follows. First, on the basis of operating pressure, that is atmospheric pressure CVD, APCVD, deposition is done at atmospheric pressure. This process has an advantage of fast deposition at low temperature, but the major disadvantage is low purity. Next is low pressure CVD, LPCVD. Reduced pressure is required for good uniformity of film because it ensures the reduction of unwanted gas phase reactions. The pressure ranges forms 30 to 250 Pascal. Next is the ultra high vacuum CVD, UHV CVD. Now here the pressure is significantly reduced up to or less than 10 to the power minus pascals. The CVD which is used prominently in modern world is either LPCVD or UHV CVD. The reduced pressure in the reaction chamber during LPCVD and UHCVD possesses enhanced the gas diffusivity, which reduces the unwanted gas phase reactions and improved coating uniformity. Next division is on the basis of physical characteristics of vapor. So here we have the aerosol assisted CVD, AACVD. In this, the precursors are transported to the substrate by the means of liquid gas aerosol, which is generated with the aid of ultrasonic treatment. This technique is employed when we have non-volatile precursors. Next is direct liquid injection CVD, DLI CVD. The precursor in this CVD is in liquid form or solid dissolved in suitable solvent. This liquid precursor is injected into the vaporization chamber directed towards the injectors. Now, DLI CVD has an advantage of accurate control of doping level. On the basis of plasma methods, plasma enhanced CVD, PECVD. This process utilizes plasma to enhances the reaction rate of the precursors. This allows the deposition at lower temperature, which is very critical parameter in the manufacture of semiconductors. Lower temperatures also inhibit the deposition of organic coatings such as plasma polymers, which have been used for nanoparticle surface frictionalization. Microwave plasma assisted CVD, MPCVD. This process utilizes a microwave plasma source. The next one is remote plasma enhanced CVD, RPECVD. This is similar to PECVD, except that in this wafer substrate is not directly placed in the plasma discharge region. This has a benefit that we can reduce the processing temperature down to room temperature. Let us first discuss the low pressure chemical vapor deposition technique, that is LPCVD. It is that chemical vapor deposition technique in which heat is used to initiate the reaction of precursor onto the substrate. In this, deposition of thin films on semiconductor substrate actually occurs in the range from a few nanometer to many micrometers. So this figure shows the schematic of LPCVD reactor. Here the reaction occurring is responsible for the formation of solid phase material. Low pressure ensures that no unwanted gas phase reaction occurs, and also the uniformity across the substrate enhances. So, as evident from this figure, in LPCVD, tube is evacuated to low pressures in the range of 10 millitorr to 1 torr. Now, when the tube is under vacuum, it is heated up to the required deposition temperatures. Temperatures which are attained in LPCVD generally lie in the range of 425 to 900 degrees Celsius, depending upon the process and the reactive gases being used. So, after attaining the desired temperature, gas is inserted into the tube. This gas then diffuses in the tube and reacts with the surface of the substrate, leading to the formation of solid phase material. Now, the main reason for choosing LPCVD in the place of APCVD is the ratio of the mass transport velocity and the velocity of reaction on the surface. Now, it has been observed that LPCVD films, they are more uniform, they have lower defects and exhibits better step coverage than the films produced by conventional PECVD and PVD techniques. Also, LPCVD is mostly employed to deposit polysilicon used for gate contacts, silicon nitride and silicon dioxide used for isolations. Mostly LPCVD films, they are with good conformal step coverage and offer good side wall protection. Plasma enhanced chemical vapor deposition technique, that is PECVD. This is the CVD process which uses plasma to deposit thin films from a gas state to a solid state on a substrate. Here the reaction involved in this process occurs after the creation of plasma of the reacting gases. This plasma is created by the application of RF AC frequency or DC discharge between the two electrodes. So the space between the electrodes is filled with the reacting gases. Through this process, we can deposit films on substrates at lower temperatures than that of standard CVD. Now, the underlying process in the case of PECVD is plasma is that state of gas in which a significant percentage of atoms or molecules are ionized. Plasmas with low fractional ionization are of great use in the material possessing, because electrons in such plasma, they are very light as compared to the atoms and molecules. So, the plasma which is used for processing is operated at pressures between millitorr to few torr. Since the electrons, they are very light, so they could be maintained at a very high equivalent temperatures, equivalent to several electron volts. These highly energetic electrons are efficient to induce many processes that would otherwise be very difficult to process at low temperatures, such as dissociation of precursor molecules and the creation of huge amount of free radicals. Another benefit of deposition with a discharge arises from the fact that electrons are more mobile than ions. Due to this, plasma becomes the most positive among the things it is in contact with. So the difference of the voltage between plasma and the objects in its contacts generally occurs across a thin sheath region. So here the ionized atoms or molecules diffuse to the edge of the sheath region. Now let us discuss the applications. It has many important applications in material deposition. It has been used commercially to deposit the following films: oxides and nitrides of silicon, deposition for a wide range of applications including photonic structures, passivation, hard mask, etc. Second is the amorphous silicon. Third is tetraethyl orthosilicate with conformal step coverage or void-free good step coverage. Next is it is used for silicon carbide deposition. It is also used for diamond-like carbon deposition. Advantages of this technique are low operating temperature, uniform coating of different shapes, good step coverage. High packing density, film characteristics as a function of depth. Less stress film is obtained. Disadvantages are precursors are toxic and so are the byproducts. Equipment is not economical. Capacity is limited. Contamination occurs from precursor and carrier molecules. Stoichiometry is hard to obtain. Next process or the next technique is atomic layer deposition, ALD. ALD is a process in which film is grown by repeated exposure of alternate gaseous species on the substrate. Unlike the case of CVD, all the precursors are not present in the chamber simultaneously, but are inserted in a series of sequential and non-overlapping pulses. In each of these pulses, the precursor reacts with the surface in such a limiting way that the reaction self-stops when all the reactive sites present at the surface are occupied. So the maximum amount of the material deposited on the surface after a single exposure to all of the precursors can be only estimated by the nature of precursor surface interaction. In order to grow uniform and high precision films on large and complex substrates, one need to vary the number of cycles. So ALD is considered to be one of the very good deposition methods which have the potential to grow very thin conformal films with controlled thickness and composition at the atomic level. Now the underlying process of ALD is, in a typical ALD process, a substrate is exposed to two reactants A and B in a sequential way such that no overlapping is there. Unlike other techniques such as CVD, where thin films grow in a steady state process, in ALD, each reactant reacts with the surface in a self-limited way. So the reactant molecules can react only with a limited number of reactive sites on the surface. So this process is schematically shown in this figure. So when describing an ALD process, one defines both the dosage times and the purge times for each precursor. The dose purge sequence of a binary ALD process constitutes an ALD cycle. Now, according to this figure, we have in frame A, the precursor 1 is in blue, is added to the reaction chamber containing the material surface to be coated by ALD. After precursor 1 has been adsorbed on the surface, any access is removed from the reaction chamber. Now precursor 2, which is red, is added frame B and reacts with precursor 1 to create another layer on the surface, frame C. So precursor 2 is then cleaned from the reaction chamber, and this process is repeated until a desired thickness is achieved and the resulting product basically resembles frame D. Applications of ALD. ALD can be used in various applications including high K-gate oxides, storage capacitor dielectrics, pinhole-free passivation layers for OLEDs and polymers, passivation of crystal silicon solar cells, high aspect ratio diffusion barriers for copper interconnects, adhesion layers, organic semiconductors, high conformal coatings for microfluidic and MEMS applications, other nanotechnology and nanoelectronic applications, coating of nanoporous structures, fuel cells, example single metal coatings for catalyst layers, biomems. And the advantages of ALD are: ALD produces film of atomically controlled thickness. Also, the growth of different multilayer structures is forthright. Due to the sensitivity and precision of this equipment, it is an asset to those in the field of microelectronics and nanotechnology in producing small but efficient semiconductors. ALD is usually run at lower temperatures. The lower temperature is beneficial when working with fragile substrates such as biological samples. Some precursors that are thermally unstable can also be used as long as their decomposition rate is relatively slow. Disadvantages are: high purity of the substrate is very important, and so high cost will follow. Though this cost is not much relative to the cost of the equipment needed, but one needs to perform several trial runs before finding out the apt conditions that favored their desired result. So it is not much economically viable. Also, ALD is a very slow process and can be effectively used for substrates used in microelectronics and nanotechnology because their thick atomic layers are not needed. There are some chemical limitations as well. Precursors which are used should be volatile but not subjected to decomposition. So this imposes a limitation on the substrates that can be used. Let us now discuss chemical solution processing or sol-gel processing. Sol-gel is a chemical solution process used to produce ceramic or glass material in the form of thin films, fibers, or powders. This method is generally used for the deposition of oxides, especially oxides of silicon and titanium. The term sol-gel refers to a process in which solid nanoparticles dispersed in a liquid gather together to form a continuous three-dimensional network extending throughout the liquid. So, a soul is a colloidal, that is a dispersed phase which is so small that gravitational forces do not exist. Only van der Waals forces and surface charges are present. Or molecular suspension of solid particles of ions in a solvent. So a gel is a semi-rigid mass which is formed when the solvent from the soul begins to evaporate and the particles or ions which are left behind start to join together in a continuous network. So students, the underlying process for this type of technique is as follows. The precursors that are used in sol-gel process are typically metal alkoxides and metal chlorides, which undergo hydrolysis. So the sol then proceeds towards the formation of an inorganic network which contains a liquid phase called as gel. Then the formation of metal oxide and metal hydroxopolymers starts in the solution. These forms because formation of metal oxides involves connecting the metal center with these groups. Then the drying process starts, which removes the liquid phase from the gel, thus forming a porous material. Then thermal treatment may be given to enhance the polycondensation and the mechanical properties. So the precursor can be used to either deposit thin films or to synthesize powders. So this figure shows an overview of sol-gel process. Applications. It is used in ceramics manufacturing process as an investment casting material or as a means of producing very thin films of metal oxides for various purposes. Sol-gel derived materials have various applications in optics, electronics, energy space, biosensors, medicine, and separation technology. One of the more important application of sol-gel process is to carry out zeolite synthesis. Other elements, metals, metal oxides can be easily incorporated into the final product, and the silicate sol formed by this method is very stable. Other products manufactured with this process includes various ceramic membranes for microfiltration, ultrafiltration, nanofiltration, vaporization and reverse osmosis. Now let us discuss the advantages and disadvantages of this process. Advantages are it produces thin bond coating to provide excellent adhesion between the metallic substrate and the top coat. It produces thick coating to provide corrosion protection performance. It can easily shape materials into complex geometries in a gel state. It can produce high purity products because the organometallic precursor of the desired ceramic oxides can be mixed and dissolved in a specific solvent and hydrolyzed into a sol and subsequently a gel. So the composition is highly controllable. It can have low temperature sintering capability, usually from 200 to 600 degrees Celsius. It can provide a simple, economic and effective method to produce high quality coatings. Now the disadvantages are, despite its advantages, Sol-gel technique possesses some industrial limitations, which are weak bonding, low wear resistance, high permeability, and difficult in controlling the porosity. Generally, the limit of the maximum coating thickness is 0.5 micron when the crack-free property is a critical requirement. Lastly, the trapped organics with a thick coating quite often results in failure during thermal process. So students, let us summarize what we have learnt in this module. The chemical deposition techniques of various kinds have been discussed. The advantages of chemical techniques over physical techniques have been told. The modern day chemical techniques like LPCVD and PECVD have been explained and their advantages over other conventional CVD techniques were discussed. Importance of ALD technique in the deposition of thin films with atomically controlled thickness has been elaborated. The sol-gel technique is explained by a step-by-step process. Also, its economic importance has been described. Thank you.